all those things. Now, claim check pattern is very interesting pattern. So I have seen many times that client is sending a message a request, and request is massive, and it is bigger than the size the message bus can handle. So the best way to is to store that payload in a store, like a storage, blob storage, and pass a reference to service bus, and then at the receiving end, the system knows that looking at the token, it will access that payload from the storage. It's not it's an exceptional flow. It's not the main flow. So this means we need to have a logic in our sending application that if the message is bigger than X size, it should go to storage. Otherwise, it's normal flow. So that is called claim check. Okay, so why it's important? Because I have seen system failing if message is too big. Either queue will fail or some other exceptions. There's another way of doing it is to compress the message and then send it. Still, that is not very good solution. I think claim check is much better than that one. It will increase the latency. However, still is good than losing the message. I will not go through the I will not go through more in detail with compensating transactions. Normally, I haven't used this in my integration. However, it could be useful in some cases. So when we use eventually consistent operation that consists of series of steps, a compensating transaction pattern can be useful. Specifically, if one or more steps fail, you can use the compensating transaction pattern, undo the work that the steps performed. Typically, you find operations that follow the eventual consistency model in cloud-hosted application that implement complex business process and workflows. The compensating transaction in Saga is very similar. The Saga-driven pattern helps maintain data consistency in distributed systems by coordinating transactions across multiple services. A saga is a sequence of local transactions where each service performs its operation and initiates the next step through events or messages. If a step in the sequence fails, the saga performs compensating transactions undo the to undo the completed steps. This approach helps maintain data consistency. So basically, if in distribution one service fails, it has to revert back all the committed services. That's very simple, and Saga this pattern helps in doing that. Um, so let's take a look at the example. So in integration spanning multiple systems, like you have Salesforce, Workday, Dynamics, and Maximo, a single transaction may involve several steps across independent database or APIs. So if one step fails midway, there is no global asset transaction to roll back. So if you remember in SQL Server, we have option to use ACID, and we can either transaction will be through or it will fail. If it fails, it will revert back everything or that transaction. So uh, in this scenario, the leaving data inconsistent or business processes stuck halfway. So if it has done, let's say in this scenario, it has done Workday Dynamics and not done Maximo, so it's not a complete transaction. So in this, for let's say another example, a customer is created in Salesforce, but Workday update fails. Now one system shows a record and other doesn't, and that's would be a problem. Now, how it will be resolved? Use Saga's a long-running transaction with the compensation logic. Instead of rollback, each step performs a local transaction on failure, executes a reverse action, undo prior effects. So you can have a orchestration layer. For example, in this scenario, you can have use Azure durable function or logic app standard to manage workflow. Each activity is a separate function or API call. So you can have a create customer, workday, update workday, notify CRM. So they are different calls. and we have compensation logic. For each action, define a corresponding undo operation. So if you're creating using a create customer, then you must have a delete customer. If you update workday, then we have the revert status. If you notify refund payment. So these are basically compensating logic for the normal flow. If any step fails, the orchestrator trigger compensation for completed steps in reverse order. Then we have messaging and state, maintain state in durable function, context, or external store, or you use service bus or event grid for event driven progress updates. Then we have observability. So we have to log all what is happening with the system, and we have to use correlation ID. Okay, let's move on to another one. Competing consumer patterns, very simple. I have taken this diagram for Microsoft website. So enables multiple concurrent consumers to process messages received on the same message client messaging channel. With multiple concurrent consumers, a system can process multiple messages concurrently to optimize throughput, to improve scalability and availability, and to balance the workload. So what is happening here is if you connect application which is generating messages directly to consumer, there's a possibility that if it's connected to one instance to another instance, it is possible that if it fails, it will fail the whole instance or might be to lose the message as well. The best way is to have all the all the application instance that generates the message, put the message into message queue, and other side of the queue is consumer services. It has its own instances as a pool. So whichever instance is free, it will pick up the message and process it. If it fails to process it, message will still be in the queue. All right, so very simple pattern. It's not a problem. Uh, I haven't used this pattern before, but I think it's a very simple. Let's move on.